Welcome to the 993rd, I should be 93rd, monthly meeting. So we are just 7 meetings away before our 1000th meeting. So we are looking forward to it. Yeah, today's speaker we have Professor Daniel Eisenstein from Harvard University. Now going to our agenda. So to begin with, I would like to mention that one of our dear members, and I think Richard, if you could speak to.
Here, bring Steve up with me.
I put the picture up here. You know, you do recognize someone sitting further out.
It's a motley crew.
Yeah.
Well, some sad news has come to us. One of our dear members, Paul Cicchetti, passed away yesterday. We don't have any details yet. His wife found him. I presume it was at home. She told me tonight that there is an autopsy planned, and she promised that as soon as details become available, she'll let us know so we can, pay our condolences.
Paul has been a member of our club
What a shock.
I've known him for about 40 years, and way back in the mid-'80s, Paul and John Reed, were kind of responsible for keeping things going. They did a lot of the structural work at the clubhouse. They re-supported all the columns on the porch. They're responsible for the trunnions that hold up the test tunnel today. They isolated that from the room and so forth. Every Saturday they were there working away, not just on work Friday weekends. So it's a real shocker. Paul had a cardiac event several years ago. He had an angioplasty, balloon angioplasty and so forth. But he had been in okay health, no events since then. Evidently he was found dead just the other day. We were with him a week ago Saturday at the work party chatting, and it was just a normal day. It was quite a shock. So any information we get, we'll pass on.
We certainly will.
At some point. So
we're not trying to steal the joy from our astronomy
Yeah.
club meeting, one of our favorite things to do every month. But we figured we better get the news out of it as it just became available this afternoon. So
yeah.
And for those who didn't know him, that's Paul in the back there with his wife, Deb. Oh, wow. Nice guy. He and John Reed right now are enjoying Mag 8 skies.
Yeah.
Oh, you guys, come on. Well, thank you all. Sorry about the bad news.
So I'll get back to the agenda. So the usual policy we had was we had the business meeting first and the speaker and so forth. So again, because it is not in our bylaws, I need a raise of hands to make sure that we are all agreeing to having the speaker come first and the business meeting afterwards.
Sure.
Thank you. I think they're good. I think I'll go straight to the speaker. So tonight we are delighted to welcome Professor Daniel Eisenstein. Professor Eisenstein is the Paul C. Mangelsdorf Professor of Astronomy at Harvard University and one of the world's leading observational cosmologists. His research focuses on understanding the large-scale structure of the universe and the nature of dark energy. Professor Eisenstein played a foundational role in establishing baryon acoustic oscillations as a powerful tool for measuring the expansion history of the universe. His work helps turn subtle patterns in the distribution of galaxies into one of the most precise standard rulers in modern cosmology. He has led several of the largest astronomical collaborations of our time, serving as director of Sloan Digital Sky Survey, and more recently as spokesperson of the Dark Energy Spectroscopic Instrument, which is now creating the most detailed three-dimensional map of the cosmos ever assembled. Professor Eisenstein also plays a leading role in the JWST Advanced Deep Extragalactic Survey, or JWST, using the James Webb Space Telescope, study the earliest galaxies formed after the Big Bang. In addition, he serves on the board of directors of the Giant Magellan Telescope. His contributions have been recognized with the Shaw Prize, and he was elected to the U.S. National Academy of Sciences in 2014. He recently completed his term as chair of the Harvard Department of Astronomy. Please join me in welcoming Professor Daniel Eisenstein.
All right, well, it really is a pleasure to come and talk today. I think I was back with this group about 10 years ago talking about work on baryon acoustic oscillations. And today I'm going to be telling you about something really different, namely work with the James Webb Space Telescope. Of course, James Webb hits almost all aspects of astronomy, but I'm going to be focusing on the topic of galaxies. And I think, as many of you know, galaxies can be really amazingly beautiful things to look at. They're also super complicated. And so as we try to understand how galaxies form and evolve, we're left trying to figure out what's going on. Now, one of the real challenges with galaxies is they're very large and they evolve over billions of years. And so we cannot sit there and watch the movie of how they evolve. I mean, if you look at a computer simulation of the evolution of galaxies, you can watch a billion years in the blink of an eye, but when you're actually at the telescope, you are just looking at pictures, snapshots. And so what we have to try to do is use the fact that light travels at a finite speed, and therefore that by looking at very distant galaxies, we're looking back billions of years. And so you can then look at collections of galaxies at when they were young. And so the primary thing we're trying to do is compare populations at different ages. So if we start with that group of people, then we can move to that group of people, that group of people, that group of people, that group of people. And we're trying to figure out what the patterns are, but you're not seeing the same person. And you're not able to connect which person turns into what. So it's actually rather delicate to try to figure out how galaxies evolve because of problems. Now, a key thing that I need to get across from the mathematical point of view is this idea of cosmological redshift. So this is the idea that the universe is expanding, and so more distant galaxies appear to be moving away from us at higher and higher speeds. And so this is the famous Hubble law that distance is proportional to velocity at low distances. But as you go to further things, you're looking at objects are moving away from us at higher and higher speed. And then the core idea is that effectively the Doppler effect shifts the wavelength of light to longer or redder wavelengths. Now, formally, it's not really best to think of it as the Doppler effect, but that's close enough for what we need to do. So this is called the red shift because it's shifting to the red. And it's denoted with the letter Z. And so light that's emitted at one wavelength, here lambda, gets received at a wavelength that's been stretched by a factor of 1 plus Z. Now, more properly, I think it's better to think of it as like the universe is expanding and it's stretching the wavelength of light. The idea being that like if the light was emitted when the universe was 3 times smaller than it is today, 27 times less volume, but 3 times smaller in linear distance, then the light's been stretched by a factor of 3, we would call redshift 2. Now, the good news is, so I'm going to be saying redshift a lot, which is why I figured I need to have a slide just to say what redshift is. So unfortunately, redshift is pretty easy to measure because when we take a spectra of galaxies, we can identify the familiar chemical fingerprints of the elements, and we can measure the shift of light with that. So it's reasonably easy to measure redshift and thereby to sort galaxies by their distance, and then sort galaxies by their look-back time. So let's get a sense of what these look-back times are. So nearby galaxies are at rather small redshifts. So if we have a galaxy whose light was emitted to us 65 million years ago when the dinosaurs were being wiped out by an asteroid, it's moving it away from us at about 1,500 kilometers per second, 3 million miles per hour. That's a redshift of 0.005. If you have light that was emitted when the Earth was formed 4.5 billion years ago, that light is coming to us from a redshift of 0.4. So these numbers are rather small. We're going to be talking about much larger numbers in terms of redshift. We're going to be interested in the galaxies that came to us from the first billion years after the Big Bang, when the light has been shifted by a factor of 6 or more. Now, these galaxies are quite far away, and they're incredibly faint. So they're billions of times fainter than what you can see in the night sky. And the faintest galaxies in pictures like this would deliver a few photons per month to your eye. And so that's why we need really big telescope and really dark skies. And even with really big telescopes, we're only talking about a photon per second. So it's a tiny, tiny, tiny rate. All right, so big telescopes brings us to the topic of the James Webb Space Telescope. This was a mock-up that they made about 15 years ago, just for life size. Okay, so JWST, it's been a $10 billion mission. It's the largest astronomy mission since the Hubble Space Telescope. And honestly, it's one of the most complex technical things humans have ever done. It is really an astonishing thing. It's been a really long time coming. It was first sort of presented in a panel report back in 1996. It was then made the top priority of something called the Astronomy Decadal Survey in the year 2000. And it had a lot of trouble in its development. It almost was killed by Congress in 2012. And not for bad reasons. Probably really had problems. But now it's been successfully launched and deployed. And even though we've waited a very long time for it, it is really an amazing transformative opportunity. Okay, so now I want to switch and tell you why James Webb is so important. And the first thing to get across here is that James Webb is built as an infrared optimized telescope. So in particular, it's really optimized for 1 to 5 micron light. So remember, our eyes see about half a micron. So it's only a little bit into the infrared. The full range goes out to 28 microns. And why do we care about studying things in the infrared? Well, the main thing for this talk is going to be this idea of cosmological redshift. That light is getting stretched out, and so the light that is emitted in the ultraviolet or optical is all getting shifted in the early universe galaxies. Are all getting shifted out to the red and indeed into the infrared. But there's other reasons why we care about that. There's this idea of interstellar dust. If you see dust lanes in galaxies, that dust is preferentially absorbing the blue light. And so if you want to look at things that are really behind large amounts of dust, there's no optical photons that are getting out, and you have to look at the infrared. We care about cold objects like planets or cold stars, and those emit primarily in the infrared. And then there's also key diagnostics that happen in the infrared. So if you have a molecule, the vibrational and rotational modes of that molecules often show up in the infrared. So lots of reasons why we like to study infrared astronomy. Now, if infrared astronomy is so great, why don't we all do it? And the reason is it's really far from the ground because, as you know, things at room temperature also glow in the infrared. And so that means that the air above you is glowing in the infrared. It means your telescope is glowing in the infrared. And so if you really want to do infrared astronomy from the ground, you're faced with the problem that the foreground emission you're getting from the telescope and the atmosphere is about 1,000 times brighter than what you would have in space. And that's at 1 to 2.5 microns, which we will grudgingly do from the ground. But once you get out beyond 2.5 microns, now this grows to a factor of 1 million. And you just can't possibly keep up with working in space. So when you go to space, you want to have a cold telescope to suppress the thermal emission from the telescope. Of course, you've gotten beyond the atmosphere. And what's left to produce foreground light? Well, it turns out that the foreground light that you see is this thing called the zodiacal light. That is the backscattering of sunlight by little tiny specks of dust out, from ground up meteorites out in the, or asteroids out in the solar system. So that little bit of haze out in the solar system is backscattering sunlight to you. But for the same reason that the sky is blue, that scattering is preferentially in the blue, and as you go into the infrared, it's getting fainter and fainter. Except that same dust also itself absorbs some of the sunlight and re-emits it, and that creates another peak that picks up and sort of starts up around 5 microns and starts to reach a peak around 10 or 20 microns. But it turns out that these two effects leave a really dark window around 2 to 4 microns. So there's a beautiful window of dark, dark, dark sky if you can get above the atmosphere and make a cold telescope and optimize for 2 to 4 microns. And it turned out that, that region is very dark, but it's also extremely useful because a lot of the properties of galaxies that we want to study at high redshift shift into the infrared at those wavelengths. Now, the problem, one of the other challenges with infrared astronomy is that, we like to use silicon detectors on the ground, such as in your cell phone, or I'm sure in the cameras that you all run. And silicon is transparent once you get beyond 1 micron, so you can't use silicon. You have to use other much more complicated and much more expensive materials. But these are now good enough that you can actually build very good infrared detectors and do it. Okay, so that's why JWST is optimized for infrared and sort of why it's so important to do infrared from space, but it is an incredibly complicated thing. And it's really complicated because it's big and it's cold. So big is sort of obvious. You're trying to launch this thing and it's big. So one of the challenges of making things cold, you have to decide how you're going to do that. You can either ship up a whole bunch of cryogen and hope that you can keep it cold for a little while, or you've got to do something passive. And so JWST sits behind this sun shield that's a fair size, basically the size of this room. And it's just sitting there in the shade out at a spot beyond the moon, I'm going to call the second Lagrange point, so that it can sit there and keep the Earth, the sun, and the moon all behind this shade and just sit there in the shade and get very cold. But of course, this whole thing is way too big to fit into a rocket. The primary mirror is segmented and all has to unfold. The sun shield has to all unfold. If you remember back to when this happened, they talked about, I think the 28 days of terror or something of all of that things that can happen to your mission. So that's really complicated. But then the other thing is they have to make things very light. So for spacecraft, basically mass is money. It costs the same amount of money to launch a brick as it does to launch something nice. And so, although the telescope is much bigger than the Hubble Space Telescope, it only weighs about 60% of the weight of HST. And one of the ways that that's done is that the mirrors are made of beryllium, a very, very light metal, also very toxic metal. So that means that when you go to polish your beryllium mirrors, you have to be very careful. But then the final thing is the fact that it's cryogenic. And cryogenic things are always really a problem because when you make things cold, they shrink. And of course, we're talking about systems that have incredibly tight tolerances, and yet they're shrinking. And one of the really nasty things about doing cryogenic things in space is that you're going to have to hold stuff so that when things shrink, and they shrink differentially, if everything's really tight and bound up together, then it's going to, it can break things. Like basically, you can sort of squeeze things and actually induce deformations that you can't, that are going to break things. But you also have to have this thing survive launch. So you're trying to hold things really loosely so that when they compress, that they don't bend out of shape. But you have to hold it strong enough that when it actually gets shaken at something like 20 G, that it's not going to break itself. So these two things don't go together, and that's a real problem for any cryogenic space thing. And of course, you're trying to reach something called the diffraction limit on a 6 nanometer telescope. So the tolerances are basically down below 200 nanometers. Okay, so if all of this wasn't a big enough problem, I think the fundamental problem, with any big space mission, if it's a flagship mission, it cannot fail. And so you have to do this massive effort to reduce risk. But now it's even more expensive, so it really can't fail. And you get into the snowballing of trying to chase the risk profile. Okay, but as you know, it was successfully launched on astronomers' best Christmas Day present ever. And Al gave me this photo that was taken at your telescopes of it drifting away from where we were with the thing earlier. Anyway, so you can see it moving away up to L2. Okay. And so after 20 years of design development, all forms of tests and all forms of work, it all worked. It's an amazing, amazing instrument. There's no mode of the telescope that is functioning poorly. Everything is basically doing what it was supposed to do, in some cases better than it was supposed to do it. Of course, it is enormously better. So this was the best picture prior to James Webb taken at 8 microns, and on the right is JWST, which is a totally new thing.
What was the aperture of the Spitzer?
85 centimeters.
Oh, geez.
So in a lot of cases, things go like the 4th power of diameter for power. So that's a factor of 5,000 better. Of course, gorgeous images. This one was the image that President Biden released to the world at the initial press conference. You can see all the gravitational lensing going on.
And those galaxies are really far away, right?
They're really far away. Yeah, I mean, basically, well, I'll show you other pictures later on, but yeah, I mean, when you see something in these pictures, like generically it's at redshift 1, unless it's further. You don't see things very nearby. Another gorgeous picture. Now, when you do look at nearby things, they're really amazing because you can look at them in the infrared and really see the interstellar media going on.
That wasn't a composite picture, was it? The last one. That's just a straight shot.
That's a straight shot. Different. I mean, I'm not sure what filters they picked for this. And every picture you take of a nice nearby galaxy has thousands of things behind it photobombing it.
Oh. Wow.
All right, so honestly, for me, as somebody who primarily works with ground-based observatories, it's honestly just disorienting to go and look at James Webb images. So this is an image taken on a 4-meter telescope at about 15 minutes over. It's a good image. Those galaxies are getting down to 24th or 25th magnitude in the optical. And there's the same thing in JWST. So that thing is that. That thing is that. Jeez. You can't even see these two. Or those two. And yeah, it just makes all the difference. And you know, part of it is you're in space with a big telescope, but a lot of it is you're working in the infrared, and all the light that was emitted in the rest frame optical has just shifted out there. Like stars want to emit in the optical and the ultraviolet, and all that light's gotten shifted out into the infrared. So it makes a huge difference. This is the deepest picture ever taken with the Hubble Space Telescope at 1.5, 1.6 microns. That's 9 days of exposure. And there's the same thing in 9 hours on JWST. Okay, so images are fantastic. They're, of course, beautiful. I encourage you to look at as many of them as you can. They're really only half of the story from my point of view. So the other big thing we do in astronomy is the idea of spectroscopy, which means taking the light from one point in the sky and splitting it up into a rainbow and measuring hundreds or thousands or tens of thousands of distinct wavelengths. And this is just critical for us because with spectra you can really measure the fingerprint of all the elements, and you can measure lots of things about the dynamics of the Doppler shifts of all the internal motions, and of course, from my point of view, measuring the cosmological redshift. But you know, spectroscopy is just a core thing that we do because that's how you really go and understand a lot of what you're looking at. And so for this, the previous comparisons of 9 hours versus 9 days don't begin to tell the story. Before JWST, we had never had access to deep spectroscopy beyond 2.5 microns. The previous mission that had infrared spectroscopy at 2.5 to 5 microns was a small satellite that was launched in the early 90s, 30 years previous, and did not have anywhere near the sensitivity to measure any galaxy, even redshift of a few tenths. So we just never could do this. And this changed completely. Not only do we get gorgeous spectra, but we do so with high multiplex. Again, most of the time, space telescopes will get you one spectrum at a time because there's like a single slit in the spectrograph and you have to get the light through the slit. But JWST has a really interesting instrument that has 250,000 little microscopic shutters and a magnet that can pass over to open up the shutters that you want to open so that you can actually take 150 or more spectra at a time. So it's just completely different. I mean, the kinds of things that we do in galaxy work at low redshift with huge spectroscopic surveys, we had no access to doing this at redshifts beyond 2 or 3, and now we do it absolutely routinely. All right, so now let me turn to this topic of studying early galaxies. So, you know, we're interested in studying the first generations of galaxies that start forming, you know, a few 100 million years after the Big Bang, when the universe is something like 5 or 20% of its present size. And, you know, on the one hand, you might say, why go to all this trouble to study the baby pictures of galaxies? Don't you have a bunch of nearby ones that you can study? We do, but it turns out that galaxy formation is really complicated, and the activity that happens at very early times has such a nonlinear effect on what's going to happen later that it's actually very important to study what's going to happen early on. But the challenge is that, as I've said several times, all the light that gets emitted in the ultraviolet optical has been shifted out into the infrared, where we just did not have the sensitivity to see it until JWST. All right. Now, it turns out that it's not just that infrared is the best way, it's really the only way. And the reason is that these high redshift galaxies are actually invisible in the optical for a reason that has to do with the properties of the intergalactic medium. So when you have a neutral hydrogen atom, it has particular, response to light, and in particular, light of 121 nanometers, a photon up in the ultraviolet, is exactly the right amount of energy to bump that hydrogen atom from the ground state to the first excited state. So if any light comes along at this wavelength of 0.1216 microns, then the neutral hydrogen will happily absorb that photon, get excited for about a nanosecond, and then a nanosecond later will de-excite and re-emit the photon, but in a random direction. So that light is no longer coming to your telescope. And so what this means is that light that is traveling at that wavelength just doesn't get through. But because of the cosmological redshift, any light that was emitted shorter than that wavelength, as it travels along in the universe, it's getting its wavelength stretched, and at some point it will come to this magic wavelength, and then it will get absorbed and be emitted and kicked out of your spectrum. So no light that is emitted shortward of 121 nanometers actually reaches our telescopes until you get way off into the X-ray. Okay, but the problem is that that wavelength of light has been shifted all the way through the ultraviolet, through the optical, and off into the infrared. So the result is that these objects have no light in the observed optical that you can actually see. They're actually invisible. So here's a picture of that. This is wavelength where 1 micron over here, and this is the spectrum of galaxy. And then you hit this cliff where the intergalactic medium has shut off the light. So this galaxy is at redshift 9.4. So the wavelengths have been stretched by a factor of 10.4. And so this light that should have been at 0.12 microns has been shifted out to 1.2 microns. Now we know that that's the redshift because here's some familiar lines. That's H beta. That's the oxygen 35007 line, and you probably have filters that will take pictures of planetary nebulae in that filter. Here it is just beyond 5 microns. So this fact that there's this cliff is the way that we go and find these galaxies. So basically what you do is you look at the sky through a variety of filters. Here's 4.4 microns, 4.1 microns, 3.5, 3.3, 2.7, 2.0, 1.5, 1.15. And you see the object until it's gone in the filter at 0.9 microns. And that is telling us that that's where the cliff is. That's redshift 8. And here's another one that's going along until it disappears in the 1.15 micron filter. That's a redshift of 11. And here's one that goes along until it disappears from the 1.5 micron filter. That's at redshift 13. So that's the way that we actually go and try to find these things. So that brings us to my project, which is called JADES. So this is a project that was a mixture of the near-infrared camera instrument team and the near-infrared spectrograph instrument team. So I'm part of the near-infrared camera team. I was a junior faculty member at the University of Arizona back in 2001, and Marcia Ricci walked into my office and said that she was going to propose to build one of the instruments on the James Webb Space Telescope and would I like to join the proposal, and I said yes. And here we are. Only took 25 years. So this basically was built off of time that was associated with the contracts to build the instrument. And it is conducting very deep imaging and spectroscopy of the two best studied fields on the sky, the Hubble Deep Field and the Hubble Ultra Deep Field regions around them. So that's what we're doing. James makes gorgeous pictures. I'll at the end give you a URL for a viewer where you can go and explore the images yourself, but it's gorgeous, gorgeous data. And indeed, we can happily find these galaxies. So here's geometry coming along and then it's dropping out. Redshift 8. Here's redshift 11. Here's redshift 13. So it all works as one would hope, but these are all candidates. You know, you don't be worried that maybe you're getting fooled by something else. So you really want to test if these are really at high redshift, and to do that, you need to take a spectrum. Unfortunately, JWST had a very sensitive spectrograph on board. So we got these first objects, and we went off and managed to get the first spectra of these high redshift galaxies. And so indeed, there's the cliff at redshift 10, redshift 11, redshift 12, redshift 13. So these were the first detections. When this object came out, it was the record holder. Now this is continuum spectroscopy at 29th magnitude, which if you speak magnitudes is crazy faint. From the ground, we're happy to work. I mean, thrilled really to get to 24th magnitude. So this is 100 times fainter than anything one ever does on the ground. Now it was 28-hour exposure, so it's pretty long. Okay, so we're really excited to see those first high redshift candidates, but we were also a little concerned because all we could see was this sort of continuum and a break. We hadn't really measured any distinct emission lines that would really conceal things, and that changed completely with this object GMZ11, which was an object that had been known from Hubble at redshift 11, and we observed it with imaging and spectroscopy. And so here is imaging. This thing's really bright. It's actually the brightest thing, one of the brightest sources known about redshift 10, I think. And because it's bright enough to be seen with Hubble, bright means 26.5 magnitudes. But you know, here it is, and boom, there it is. So it's really, really sharp. So prototypical high redshift dropout. But the spectrum is gorgeous. So now you really can see all these emission lines, you know, tremendous break, but all these emission lines. So there's the 3727 line, for example. So there's over a dozen well-detected lines that seals the redshift at 10.6. So what is GNZ11? It's probably an AGN, probably an active galactic nucleus, a black hole accreting stuff. It's not rock solid proven that that's what it is, but very likely. So that would produce a black hole mass of something like 2 million solar masses. Interestingly, it may not be alone. We see other candidates in the field at the same redshift nearby. So we're kind of interested in whether there may be shown clustering. So to put a sense on this, this is a plot in redshift or photometric redshift, estimated redshift versus magnitude 25, 27, 29. These are what was known from Hubble. And again, these are the best studied fields on the sky. So there's GMZ11 there, and then the candidate at redshift 8. That was before JWST, and that's what we found in our first data set with JWST. So you just really completely unlock the ability to get to high redshift. Again, these are all photo candidates, but we already got some spectra of, at this time it was 42. It's now a little over 100, and there's no catastrophic failure.
Can you back up to the previous slide, please?
Yeah, sure.
That well-defined line at 8, is it?
That selection, that's just where we chose to cut the catalog.
Okay.
Yeah, these are still needles in a haystack. Most of, the average thing in the field is redshift 2.
Okay.
Yeah. Oops, sorry. So when we were just developing the telescope, we kind of figured that these high redshift galaxies were all really small. They are, but they're really, we thought they'd be so small that you couldn't really see any information about them. They'd just be point sources. Turned out they're not all point sources. There's a bunch of them that are well resolved and show complex shapes and multiple bumps, and so there's a fair bit of things going on in terms of the early hierarchical structure. That's even true at redshifts above 10. Like some of these that redshifts above 10 are resolved.
What kind of angular resolution is that?
Oh, okay. So the pixels on JWST are 0.03 arc seconds. And the full width half max is basically twice that. So they're about 0.05 arc second images. It does vary with wavelength, but I think that's the good number to run on. So we now have in the field over 2,000 of these candidates beyond redshift 8. And there's hints of clustering, and the early universe has lots of interesting behavior in it. We can actually measure enough spectra that you can actually start to see that really redshifts do cluster up. So this is according to the field now with spectroscopic redshifts 5.2, 5.3, and then there's a lot of galaxies at 5.4. So we're actually seeing clusters at high redshift. And that's been a really interesting aspect of JWST, is seeing how clustered, this was expected, but seeing how clustered the early galaxies are. Yeah.
Earlier, somebody asked what you meant by catastrophic failures. You said no catastrophic.
Oh, meaning that we thought the thing was at high redshift, but it turned out to be at low redshift. That we just, that mistake on the redshift. All right, we also now have thousands of these spectra of faint galaxies. And again, here's the galaxy I showed you earlier, but now with even more exposure time. So this is now up to 75 hours, so 3 days of exposing on this one object. But a very, very clear detection. Okay, so clearly we're seeing that we're seeing that there's a lot to be seen, and I think that's the important thing. There's really a lot of available information. So in addition to the fact that the images themselves, the morphology of the galaxies is complicated, we see variations in their spectra, in their spectral energy distribution, in the ratios of their lines. We're seeing evidence for variations in star formation histories. We're seeing evidence for variations in the abundances of different elements. So like some galaxies have more carbon, some galaxies have more nitrogen. That's telling us about the nucleosynthesis in the supernovae that are in those galaxies. So there's lots of things to be done. And I think that's just really one of the most important aspects is that in the first year's missions, we've shown that there's a lot to be studied. And people, of course, are digging into that quite a bit. Okay, so of course, having turned on the telescope and quickly found galaxies at redshift 10 to 13, we were really, trying to figure out, where does it stop? How far back can you go? And so in the second year, we were approved to return to one of the year one fields to produce very deep images in what are called medium band filters, so narrower wavelength ranges. And the goal here was to try to find galaxies out perhaps beyond 15. And so this one pointing, which we now call the J's origins field, has been stared at for 10 days with the telescope across 16 different filters. So it's really an extraordinarily deep image of the sky. One of the fun things we do with these medium bands is really look for emission lines. So this is a false color image, of course, is everything I've been showing is false color, but this is false color with filters at 0.9, 2, and 4.4 microns. So that's sort of a broadband sense. And the next picture I'm going to show you is now three very tightly spaced filters that are narrower, with the green filter, the green color on the screen associated with a medium band of 3 microns. And you see that a lot of these galaxies turn interesting colors when you can look at very adjacent filters, and that's showing you that there's very strong emission lines perturbing the colors. Okay, so now I'm going to spend the last bit of the talk telling you about this galaxy up here. So out of all galaxies, we're going to pick on that one. And you can see it's very red in these colors. And this got us interested. So this object was originally flagged as a possible F-150 dropout. You look, the right-hand component is there, until it isn't. Okay. But we looked at it and I'm like, not really sure, because it has this neighbor. And like, is this neighbor is clearly at low redshift because it's visible all the way down to the left. And we just were not confident that this dropout on the right might not be some behavior of a low redshift galaxy that we hadn't quite anticipated. And it's only after we got the even deeper imaging and the more refined imaging in year 2 that we really got the confidence to try to take spectrum of it. And sure enough, it did work out as we hoped. So here's the galactic break. And so this is now at redshift 14.2. So when this came out, this was the record holder. It's now been surpassed by one other galaxy of 14.4. But it's still a really amazing galaxy. And so let me tell you why it's such an amazing galaxy. So it's really surprisingly luminous. You can sort of see it pretty well on those past images, which is already telling you that it's not super duper faint. And so in practice, of all the galaxies we found at redshift greater than 8 in our year 1 data, it's the 3rd most luminous galaxy. And that's really strange because the early universe, gravity is pulling together the dark matter. It's just getting the process started, and things are growing really quickly. So when you go from redshift 14 to redshift 12, the number of dark matter halos at a given mass increases by an order of magnitude, a factor of 10. Come to redshift 10, now it's gone up by a factor of 100. Come to redshift 8, it's gone up by a factor of 1,000. So what I'm telling you, there's 1,000 more places to have galaxies here than there are here. And yet, it's the 3rd most luminous. So if you make a model that says, well, galaxies should maybe get brighter in proportion to how massive their halo is, you would predict, like the simplest model you would make, would predict curves that would go like this. And you can see that if you see things here, you would be expecting to see things up here, and we just don't. So it's really weird. Now, also, it's very interesting that it is angularly resolved. It is not point source. And that's important to me because if it's a point source, then it could be due to matter falling on black holes. And I don't understand black holes, and nobody really understands black holes. And so if you want to drop a lot of matter on the black hole and make a whole lot of light, nobody can tell you you're wrong. But when it's resolved, that means it's due to stars. And that means it really is something about how you're going to bring together a lot of mass. So that's a very important aspect. Also, interestingly, is that if you might imagine if it's like a very early galaxy, it's the earliest galaxy we found at that time at least. And do we expect it to be formed entirely out of young, massive, very blue, very hot stars? But this galaxy is not super blue. The spectral energy distribution actually indicates that there's a fair bit of interstellar dust. We didn't think dust could form this quickly, but apparently it does. And we now know that the chemical abundance, what we call the metallicity, is not incredibly low.
Yeah.
It's like 10 or 20% solar.
Wow.
So we were out looking for baby galaxies and we found a teenager. It's not, it's a young galaxy. It's less massive and so forth, but it's not a baby. Which means the babies are out there somewhere beyond redshift 14. We just haven't been lucky enough to find one.
Am I ever gonna see a pop 3 star?
Well, a pop 3 star? Probably not. We hope we'll see the impacts or the effects of pop 3 stars. Okay, so this isn't the only galaxy at redshift 14. There's another one that we have in our field about redshift, the 14.0. We do have a spectrum of that, so that's been proven. So there they are together. Okay, so let me wrap up. JWST is really revealing large populations of galaxies at high redshift. And I think a really interesting thing is that these galaxies are not homogeneous. So if you had some picture, some cartoon in your head of, oh, galaxies are going to do this, Well, some galaxies do that, but other galaxies do other things. And so it's really that diversity that I think is very interesting. And there's just really marvelous opportunities out there. So I want to really encourage you, we can even take some time to do it ourselves, do it together, but there's a really awesome viewer here at this URL. I'll pull it up here in a second. But you can really, it's really, really cool to play around with. Oh yeah, I forgot this example. Here, this is a complex of redshift 7 galaxies. Here they are 1.15 microns. Here they aren't. The whole thing, the whole set drops out. Okay, so to conclude, the redshift frontier is now out beyond redshift 14. And this galaxy is really extremely luminous and very interesting. Like either the earliest galaxies are really, really, really efficient at using their light, or we're actually missing a population of galaxies at redshift 8, maybe because they're all dusty, or we got super duper lucky. And I think this one object is really, you've read in the papers a lot. They're like, oh, JWST is finding all this extra population of early galaxies. And frankly, some of that is clickbait. But this object is like the best proof of that narrative. That's really the early universe got going more earlier than we thought. So I really want to thank the whole JADES team. We have a number of people here at the CFA working on JADES, but really it's a big collaboration, both in the US and in Europe. And I really want to thank the thousands of people who made JWST a reality. When you talk about a project costing $10 billion, I think a good way of thinking about what $10 billion is that if the average salary is $100,000, then $10 billion is 100,000 person years. So that's 10,000 people working for a decade to make the project work. Okay, so I mean, JWST, for my entire professional life, there have been many questions in galaxy formation for which the answer was, we'll have to wait for JWST. Like you just couldn't do it. Like there's no amount of, you know, elbow grease or stick to itiveness that would fix the fact that you're facing a factor of 1 million background on the ground. So we've been waiting decades, and it's totally working. So our data release is here, and so that's the URL. Sorry, that's the QR code to go and get to this viewer. Or actually, I hope that's still working. Maybe it's not. It's a little tired. But let me go and pull this up so you can see it. The screen is probably not going to fully do it credit. Well, you can zoom out here. So you can zoom out and then zoom in. But there's a lot of ways you can then manipulate the data. So if you come over here, there's a whole bunch of things you can look at. Different RGB combinations. You can look at the individual, look at individual filters. And I really like turning on the RGBs that are the adjacent medium bands. If you come to the second thing, you can turn on you can turn on these little dots, which when you go and click on them, they will actually pull up the thumbnail so you can see the photometry in situ and the photometric redshift that's estimated. If you click on the spectra, we go around and find the spectrum too. Then you can go and see the spectra of objects that's been taken. After click on one redshift 3.35. So there's really lots of things, lots of ways. I think it's just a very interesting way to get familiar with, like, if you haven't actually had a chance to browse what galaxies in at high redshift really look like, I think this thing really does allow you to do it and to just play around. And you'll find, it doesn't take you very long to find things that are really unusual. Here's one of my favorite examples. We call this the cosmic rose. And there it is in the broadband filter, but when you shift into the medium band filters, you see all this emission of certain galactic gas emission. This is actually the H alpha emission line at redshift 3.5, showing up at 3 microns. So I think it's a really fun way to look at the sky. Okay, and I will maybe go back and I don't know if anybody's actually checked whether this QR code still works with that, but and maybe I'll give it to you so you can put it in your next newsletter. So you can, okay, yeah.
Right.
Okay, so yeah, thanks very much.
So two quick questions. One is, about how much time does James get on the JWST?
So the original program was 800 hours. So that's like a month. So yeah, no, it's the largest program that executed on the telescope. I think it's the largest program that has yet executed on the telescope. It was the largest program in cycle 1.
That's what.
Is that 800 hours?
It doesn't quite work.
That
Or,
was deactivated.
yeah, okay, I have to get a new one. I'm sorry.
That per year, 800 hours per year,
No, that was the block of time we were given.
over what period of time?
Well, it was supposed to be in a year, but then they decided it was too big to schedule, so they split us up into 2 years.
That's kind of redshifted.
And then, yeah, it did get redshift. And then, of course, not everything always happens the way you want. So when the telescope malfunctions for any reason, then you may have to wait a year. So in practice, we got our last data in year 3.
You never have any cloudy nights.
Yeah, no, I mean, look, it's you know, we were a little perturbed when they delayed it because originally because like didn't think it was such a great reason that they decided they delay it. But in the end, the fact is, if we had gotten all the data, you know, all at once, it would have been such a fire hose. We would not have learned in the right way to actually make best use of the second portion of this. So it was probably all for the best, even though it did cause us quite a lot of consternation.
There were some questions about what a Z of 14.5 would be in billions of light years.
In billions of light years from us. So it's not, so distances in cosmology are funny. And so in a sense, if I tell you that the universe is 13.8 billion years old and you're looking at something that's 300 million years after the Big Bang, the light has traveled for 13.5 billion years. And so it has traveled 13.5 billion light years according to its rulers as it went along. But of course, the universe has expanded in that time. And so the distance that object is away from us now is considerably larger. That's closer to 20 billion light years. But that would involve moving tachyonically, so that's not really the useful answer. So it's like, this is like the standard way to confuse undergrads is to try to teach them about cosmological distances. But it matters, like it totally affects what you see. But I think maybe the more useful way to think of it is not in terms of distance, but in terms of look back time. And that's 13.5 billion years.
Yeah. So the comment I made earlier about lensing, maybe I don't understand this, but when we're looking at galaxies through, lensing, are they even more distant, redshift wise?
Let's see.
In other words, is the lens sort of helping to magnify
The
something?
lens is totally magnifying things.
Yeah.
So you should imagine that, we're over here, there's this big massive cluster, and that might only be a redshift 0.3 or 0.5. It's not super far away. Well, it's far away, but not by the standard we're talking about. And then there's galaxies back here, and redshift 2 or 10 or whatever. And the light that would have gone straight to us, instead, we're seeing light that came above and got pulled back by the cluster and came back down. And that's what's causing the lensing. But it also causes that magnification.
So I guess what I'm asking is, if you're looking through the lens, can you see things that are even more distant than if you weren't looking through the lens?
Correct. That's right.
Okay.
So what I would really like to, how I would really like to say is that you're able to see things that are fainter
Yes.
than you would have otherwise seen. Whether they turn out to be further away is sort of there, it depends on what you're looking at.
I see it.
But they're absolutely are fainter. And, it depends on where you are in the lens. Like if you sort of imagine a lens like there, you can find the sweet spot where you can get a lot of magnification, factors of 10 or 20 or even 50 or 100, or you can really get a lot of magnification in some cases.
They're still able to do spectra and all that?
Yeah, sure. I mean, the lensing is just creating an image for you, and you can then go and take that light and dissect it the way you otherwise would. I mean, in other words, the telescope doesn't know that the light was lensed. The telescope just thinks, oh, photons, I'll do something with them. So yeah, no, it's extremely helpful. The challenge about magnification. So the good news is things got brighter. The bad news is that the region in the universe that you are looking at has gotten smaller because it got magnified. So you don't automatically win. Like you have seen fainter objects, but you've seen a tiny region of the universe. You may or may not find objects there that you want to study. So sometimes gravitational lensing is, it is a very interesting thing to do, to use these gravitational telescopes, but it's not the only way to do things. And in practice, we opted not to do it because only when you look at a lens, only a little bit of the region is really high magnification. But basically, I would say in the JWST world, there's been a group of people doing non-lens fields, blank fields, and there's been a group of people doing lens fields, and they both have their merits. And so actually, I really think it's been working out well that we have a lot of both. I'm part of a program that's now doing 60 lens clusters. So if you saw that one, there are 60 more like that, and that makes them really awesome discoveries.
A quick question, does the Webb telescope have the capability to go deeper than C14?
Yeah, so that's a good question. I should have said that more carefully. So the object that we saw, the object that I told you about, is 10 times brighter than the detection limit. Like we easily would have seen it if it was further away. We would have seen it at redshift 20 very easily. We didn't. They're rare. And we don't know yet. We have not yet found a candidate beyond redshift 15 that has been spectroscopically confirmed. And even when I talk about the candidate from the photometry, like we see some things at 15 that look like, that's a good shot at being real. At 16, there's like 1 or 2 or 3 that are like, that's probably real. And nothing beyond 16 in our field or any data that I've yet seen that I would say that looks probably real. I'm seeing a lot of things that like, I don't really think it looks pretty scraggly to me. And people are publishing them and making big claims, but in truth, I don't actually. We're having a bit of a discussion. Yeah. So we of course hope that we will find things at higher redshift. When people continue to look, and we have in our last paper, we have a candidate at redshift 18 that nobody in our group thinks is a gold-plated candidate or even a silver-plated candidate. It's sort of hoping to get to bronze, but we happen to have a spectrum of it, which is not nearly deep enough to decide if it's real or not.
Do you have enough data to determine if these really distant objects are active galactic nuclei or stars? Are there separate populations that you see? So
sometimes the active galactic nuclei make themselves pretty obvious. And so active galactic nuclei is when you're dropping gas onto a black hole and it gets hot and glows. And sometimes that's very clear. So great, you can say I found one. The problem is there's a lot of times when it's not very clear. And so when you just see an object that's very compact, point-like, and bright, you're like, not sure. So you're then hoping to tease out some very subtle features to try to decide if it's an AGN or not. And so we're kind of in that state where like we have found some things out there we're sure are AGN. But there's others that we really think probably are, and we're trying to figure out.
Is the existence of AGNs that far out? Is that a surprise?
Oh, that's a really good question. Yeah, no, it's indeed. So, yeah, it's this fun little thing. Like, when do black holes in the universe actually form? And why can you get these really massive black holes? And so at low redshift nearby, there's a very interesting relationship that the mass of a black hole is about 1,000. It's on typically about 1,000th of the mass of the bulge of a galaxy. So there's a pretty tight relationship, not perfectly tight, but a pretty tight relationship between the size of the galaxy, or the mass of the galaxy in terms of stars, and the mass of the black hole. And so you would really like to know, like, did they kind of co-evolve into that state? Or did the black holes get going earlier? Or did the stars get going earlier and black holes catch up? And we are, I think, in JWST seeing a lot of interesting part of that story where we are finding some examples of galaxies at high redshifts with particularly massive black holes. So I would say that right now, the betting money would be that black holes get an early start. And we're trying to figure out if that means that they really start from stellar mass objects, stellar mass black holes that then manage to really grow a lot, or whether somehow they actually get started from higher mass and don't have as far to grow to get to the masses that we're seeing them at.
How does your work lead to better understanding of the dark matter, dark energy? He said.
So what I've been telling you today really doesn't have anything to do with dark energy. Dark energy really comes to dominate the redshifts of order 0.5 and below. It, in principle, could have things to say about dark matter. We don't really yet know yet. So, we have good reason to think that galaxies grow inside of dark matter halos. So basically, you have to gather a lot of material, both dark matter and gas, together. And the reason the gas can actually get to high enough densities is because the dark matter is pulling it together. Okay, but so in principle, we would like to know enough about these early galaxies, actually measure how much dark matter is actually around them. We have not yet been able to do that in a way that I would believe. I'm hoping my student project will actually get us a first handle on this, but it's hard because, as you likely know, with low redshift galaxies, the galaxy rotating. But to really see dark matter, you have to go a fair ways out to really see the flat rotation curve and show that what most of the mass that you're seeing is due to dark matter. And that's for stellar populations you think you understand. So the problem with high redshift is these things are really compact, and you're mostly seeing the inner parts of them, and you just can't get enough leverage on the dynamical mass. But they're starting to make some progress on that. Yeah.
You're talking about getting dust absorption and emission in the plane of the ecliptic. Do you do any better when you go at a right angle or?
Yeah, that's right. So indeed, both of these deep fields are chosen to be at high ecliptic latitude, exactly for the reason you say. You want to look. You try to look, of course, away from the galaxy, but you also want to look away from the ecliptic.
Okay.
Could you say more about the spectroscope? I'm very impressed that you could, in space, have a spectroscope that you could do 150.
Right. I mean, those astronauts, they're up there. They're looking. No, it's an amazing thing. The instrument's really awesome.
Do you take an image first of the correct?
You need to know the astrometric position of your targets quite well. Ideally to 30 milliarc seconds or something. So you need to know that. And so normally you pre-image. Ideally you pre-image with JWST. In principle, you can pre-image with other telescopes and hope that you can get the astrometry to work out well enough, but mostly you would prefer pre-image with JWST. And then once you've decided on the array of targets that you want to do, you design which of these shutters you're going to open up to let the light through. And so there's, as I said, there's 250,000 little shutters, and there's a magnetic bar that sweeps across and can open up any pattern of shutters that you want. And then the light is coming from the telescope, coming to a focus at this shutter plane. So only the light from the objects you care about passes through, and then you're off to a spectrograph where you're gonna recollimate the light, disperse, and then focus again to bring to the.
Is there any fiber optics involved in
that? No. It's all all multi-slit, if you are familiar with that. Now the downside relative to so if you're on the ground and you're building a multi-slit spectrograph, then usually you have a milling machine where you are basically taking a piece of metal and you laser cut the holes that you want. And that's really nice because you can do any registration of things you want. These shutters are all on a grid. So a rigid grid. So that means that you can't actually observe all the objects that you want because sometimes they're going to fall in the center of the grid and sometimes they're going to fall on the edge of the grid. So you kind of have a natural undersampling or underperformance because of that. So if you just walk in with a set of targets and say, I would like to observe these, you get something like 30% of them that are actually well aligned to the shutters and a bunch of other criteria that you want to satisfy. So it's inefficient in that sense, but there are lots of galaxies that are lots of things to look at.
Do you turn the 2D image into a 1D image for the spectrograph, or? If you line up to line up the targets in a line, then put it into the spectrograph, or is this?
No, well, so the targets are where they are.
Yeah.
And what you're doing is you're opening up shutters that are not just in a line. So it's not a single long slit.
Right.
It's a whole bunch of little slits.
Like the Sloan survey, they moved the fibers around, and
Right.
the other end of the fibers are all lined up.
Correct. That's the wonderful thing about fibers is that you can take a arbitrary 2D configuration, and but by the time you go through all the magical fibers, you can get it all aligned into one line. That makes the fact in spectrograph much more, let's say, efficient or more effective. But here, no, that's not the situation you're in. You're going to deal with the fact that any given object is sort of, if you didn't disperse, you would be imaging 150 little shutters on a 2D image, and only then when you disperse, you turn them into rainbows. But that means that a given wavelength position is not at the same column of the detector all the time. But you solve for that, so that's okay. That's
like an objective prism.
It's like an objective prism. That's exactly right, except that you've masked out 99% of the sky. We also have modes on the telescope which really are what we call slitless spectroscopy. So that is much more of an objective prism idea. It's not literally an objective prism, but that's the idea of like really instead of a filter, you put in the disperser, and now every point on the sky has gotten stretched into a rainbow, and you deal with that. But that's actually turned out to be awesome too. That works really well.
If there's a question about, unlike the Hubble, where you could actually change out some of the instrumentation, the shuttle to get there and so forth, JWST, that cannot be done. What can be done here to refine the data in the future and going forward? What can you do to perhaps increase the sensitivity of the spectroscope, instrumentation? Anything or?
Limited things. So we are definitely learning about, let's say, more clever ways to use the instrument for certain purposes. And so, for example, one of the things I've been working on and proposed for this upcoming cycle is a way of trying to get to ultra-high multiplex, where basically, instead of 150 objects, you actually open up 2,500 objects and just let them all overlap, and then figure it out by other means, which can be done. So that's a way of, in principle, for our particular science case, which is not everybody's, cup of tea, but for our case, we think we could increase the performance by a factor of 10.
Yeah.
That'd be great. But it's, that's for a particular thing. I'm sure the folks who are doing like coronography, so that there's a bunch of these instruments that can do coronography, and that's a very subtle game. And I suspect that they are continuing to learn ways to do better and better subtraction of stars to find faint planets near stars.
Right.
We are always trying to improve the calibrations, and I think getting probably a little bit more bold in what we think we can actually calibrate. That's the matter for the imaging so much. The imaging pretty bread and butter, but for the spectroscopy, I think we're finding ways of sort of eking out more performance. A lot of that's about learning the personality of the detectors. If the detectors were all completely like, oh, every photon just generates a count on disk. Like, that would be much simpler, but in fact, these infrared devices have a lot of well, they're way better than they used to be, but there's a not small amount of instability in them. They're just not nearly as well behaved as silicon devices. Like, silicon devices today are almost, boring. Like they're almost perfect. That didn't used to be the case, of course, but now they're really, really good. And infrared devices are like CCDs from the 90s. They have a lot more, like, they show a lot of persistence. If you are a CCD person, you probably don't even really know what persistence is, but here you do. Lots of ways. Yeah.
25 years.
Yeah, so, I mean, the last decadal survey recommended something called the Habitable World Observatory. So this would be a large optical telescope worked out about 2 microns. And that's to do extremely high contrast imaging of stars to look for habitable worlds, but also to, it's like a super duper Hubble, bigger and sharper images. So that's the next thing that's on NASA's roadmap. Sorry, the things that are sort of out in the fairly far future. The very next thing on NASA's roadmap is the Roman Space Telescope that will launch later this year. But indeed, I mean, I think one of the challenges we have in astronomy is that these big missions take a long time to happen, and there's enough different parts of astronomy that can only be done in space that if everybody's waiting for their turn at the flagship mission, you have a major workforce continuity problem. So here at CFA, we run the Chandra X-ray telescope, which of course was launched back in 1999. And so, the CFA is really one of the hubs of X-ray astronomy, but there's not a next Chandra on the plans right now. And so at some point, Chandra will stop, and there'll be a whole bunch of X-ray astronomers who will not have a mission that can actually supply them with data. And you can sort of imagine what, this kind of whipsawing is really, it's very understandable why it happens, because these missions are very expensive, but it also is a very big challenge for the field of how to deal with these variations of capabilities. So with JWST, I think one of the really exciting things, like JWST was built to work for 5 years. Like the requirement was to work for 5 years. The goal was to work for 10. But the launch was so perfect that they saved enough fuel. Mm-hmm. The fuel was the only thing. They actually shaved enough fuel. I think they can launch for 20. And this is a huge, it's four times, but sociologically, it's even more important, because if it's 5 years, you can do your PhD thesis on it, and then you don't know what you're doing. Mm-hmm. If it's 10 years, you can do your PhD thesis and hope that you can get to your first junior faculty position, but then you don't know what you're doing. But if it's 20 years, you can actually have a career. Yeah. So it really does. So we're hoping, of course, it could fail. It could have just failed 5 years ago. Hold on, I didn't jinx it. But we think it's last for 20 years.
So do you wish you were 20 years younger?
Probably we all wish we were 20 years younger. Not necessarily. I mean, we're I don't know. The past 20 years from cosmology has been pretty awesome too. So
Yeah,
I'm glad you're sure.
Your PhDs, it must be pretty awesome fun.
Thank you.
Any last questions?
Ken.
Yeah.
Well, Glenn, we've missed you.
Good to be back.
Good to see you. It's good to have you back.
And it may take a moment. Just want to thank the ATMoB members who have sent me cards and emails of condolences, and also just for being being here, members of this club, because this is one of, as far as my recovery and everything like that, this is one of the positives, something to look forward to in the future. So it's great to be back, and good to see you all. Thank you.
My observing buddy here. All right, I'll completely mess this up. Anyway, let's get going. So there's some really cool things to look at this coming month. And I want to make sure you all know that it's possible, even though it's embitterly cold, it's possible to go outside and observe. You just have to dress for it. Mercury is making a bit of an appearance this week, actually. By next a week from today, it'll be at greatest elongation east, about 16 degrees above the horizon at sunset. So you may want to go out and take a look at that. Venus is currently at minus 3.9 magnitude, 9.9 arc second apparent diameter. Remember, it's on the far side of the sun. So it's really, really far away. It looks really tiny in your telescope, but it's almost perfectly round because it's 98% illuminated. It's 9 degrees away from the sun today, and it's following the sun. So if any of you were afraid to try and look at Venus in the daytime when it was preceding the sun, now there's less to worry about. 10 degrees is like 20 solar diameters away from the sun. I encourage you to go out and check it out. Just be careful, but it can be done. And here's a sky safari shot of what it looks like these days, this week, with Venus and Mercury just above the horizon, just in the west-southwest above the sun. Tricky observation if you're going to wait for twilight. You really need a spectacularly clear view to the horizon in order to see these guys. So they're better to look at them in the daytime. So I would certainly encourage you to do that. Here we go. Saturn, setting at about 8 o'clock these days. Running out of time to look at Saturn during this season. The rings are tilted about 3 degrees. Solar conjunction is like a month away. So get your Saturn now while you can. You have to wait a while to see it. Neptune is still only a degree away from Saturn at magnitude 7.9. So it's still a relatively easy object to find. Let me see if I can find the laser here. So there's a laser on this thing, isn't there? I got it.
I believe there is.
So these 3 stars here are visible in most finder scopes. So from Saturn, we can look for these guys here. These may be a little bit faint, but if you can find this star and those stars, you can hit on Neptune. Pretty cool to see. If you've never looked for it before, I would again encourage you to go out and take a peek at it. If you're we're running out of horizon at the clubhouse, and the 25-inch observatory is pretty close due to the snow and ice. We're very much afraid that it will freeze in the open condition. That's happened before. It's not pretty. When you've got this, see, what do you think the roof weighs? Like 3 tons?
Yeah.
When you've got like a 3-ton roof that's frozen open, it's really hard to get that moving again. Yeah, so we're a little reluctant to roll that roof back just yet, but spring is coming. Anyway, onward. Photo op coming up on 19 February, a week from tonight, when the waxing crescent moon, filled with Earth shine, will be very close to Saturn and Neptune in the sky. So do go out and look at that. I love looking at Earth shine. So some of my earliest memories of things astronomical were getting out of the family trucks there in the early evening in the springtime, and by chance seeing that crescent moon hanging over in the western skies with the bright Earth shine. I love it when it looks like that. So again, do try to get out to see that. Uranus at magnitude 5.6 is transiting at about 8 o'clock. It's about 5 degrees away from M45. It's an easy find because all you have to do is get to M45, come down to these little stars here, 13 Tauri and 14 Tauri. They're like 5.7th magnitude, so they show up in your finder scope, and Uranus isn't far behind. So finding this triangle is a nice, easy way to lock into the planet Uranus. Then Jupiter, of course, is the big guy this month, minus 2.6 magnitude, 45 arc seconds, transiting about 9:30. It's still pretty high up in Gemini, so about 90 degrees above the horizon. And again, I hate to beat the drum again, but do try to look at the diameters of the moons. Go out and look at the moons. Steve, we were at the clubhouse a week ago. You had your 4-inch Takahashi, and Phil, you were there with your telescope, but we watched Io move in front of Jupiter. And you could clearly see Io as a disk crossing in front of the planet. We cashed in on the fact that Jupiter has a bit of limb darkening. And so the contrast is really nice when a moon like Io begins to transit across the disk of the planet. And so it gives a nice opportunity to see the moon as a moon. You sometimes lose it when it gets out in front of the planet because the contrast drops off. But pretty fun stuff. And while we're talking about the moons of Jupiter, there's another opportunity to watch a Callisto transit coming up on February 28th. Relatively convenient, 10:15 at night. It's such a cool thing to see because Callisto's albedo, its reflectivity, is only about 20%. It's really dark. And so it silhouettes nicely against the brightness of Jupiter's cloud tops. So the first time I saw a Callisto transit, I thought it was a shadow transit. I thought I'd messed up the times because I was like, I didn't expect a shadow transit. And then when I checked it on the Sky Safari, it was like, no, that's the moon crossing in front of the planet. So that's kind of fun. The next one after this will be on March 17th. Then the lunar highlight of the month is the lunar eclipse coming up. So on the morning of Tuesday, March the 3rd, in the wee hours of the morning, the moon will enter eclipse. The umbral phase begins, the partial phase begins at 4:50 a.m. Eastern Standard Time. Totality begins at 6:04. And about 15 minutes later, the moon will set for observers here in the Boston area. So in order to really appreciate this lunar eclipse, get in a plane and go to San Diego, or you can find a really clear view that looks to the west, and you can check it out. It's going to be interesting to see how long we'll be able to actually see the moon in the sky, especially at the onset of totality. Remember, the sun is exactly opposite the moon in the sky that day. So as the moon is sinking down to the western horizon, the sun is coming up right behind you. Your shadow will point right at the moon. What it means is that the totality will occur in a bright sky. If totality is especially bright, we might have a good chance of seeing it. If not, it'll just melt into the daylight. Now, a similar sort of circumstance. This is a shot I took of an eclipse back in 2018. Anybody remember it? I called it the 17-minute eclipse because the partial phase began and the moon set.
Sorry, I was in California then.
You probably had a much better view than we did. I don't know if you remember, but this was a bitterly cold morning. I was especially grateful that the eclipse only lasted a little while, so I could get back in my car and head home. I love the atmospheric effects here, and that's not right. Help me, Benno, help me. Wait a minute, I'll get back to it. Help me, jump ahead, go way ahead. Pesky little button. And one more. There we go. So anyway, I like the atmospheric effects there. That was a fun little eclipse over the hills of Milton. Then, a fun multiple star of the month is the trapezium. You all know where it is, right? That's easy to find. But the challenge is going to be that I want you to look for the 5th star and the 6th star. Now, the challenging part is they're not particularly faint. The E and F stars are about magnitude 10.6, 10.7. Easy peasy, right? Except for the fact that they're sitting only 4.5 arc seconds away from this star and that star. And so this one's a little bit wider, 4.6 arc seconds. The delta magnitude is 3.6, which is about 30 times its brightness difference. That's an easy one to spot. The 5th star is relatively easy. It's the 6th star that's a little more difficult to see because the separation is a little bit closer and the C star is about 100 times brighter than the F star. So what you need is a steady sky. If you have a nice steady sky, you should be able to see those D and the F stars. And so that's the challenge. If you've got a massively monster telescope, there's a star in here, a pair of them, there's another one out here. The images can scoop those up in a second, but visually, I've never seen the.
This one's about 14, this one's about 16, and it's actually a tight double star here.
Yeah.
They're about 15, 16th magnitude.
They're hard to see. I think the overall brightness of the trapezium stars makes it especially difficult to see those really, really thin stars. Anyway, that's the double star of the month. And then, oh man, what is this? Okay, the challenging variable star, R Geminorum. Len, tell us about R Geminorum.
I haven't seen it in about 40 years.
Okay, go there.
No, this is actually, it's a Mira type variable star. It does have it gets pretty bright when it's at its brightest. And again, what's happened with me is I went from the Myra type stars over the years to the cataclysmic variables. So a lot of that, I haven't been paying attention to the Myra type stars. Got to get back in the game.
A light curve shows that it's got a period of like almost exactly 1 year. So, you know, this was published the other day. And so here we are right here where the star is approximately magnitude 10. But in just, you know, a month, it'll be up to magnitude 7. So it's a fun star to look at if you are so inclined. It's a nice red star. It's not the red star in the sky, but it's redder than Vega. So
I'm very embarrassed to hear him wearing an AVSO shirt. I haven't seen the star in 40 years.
That's all right. You've still got it in your notebook. The reason I mention it is because it's relatively easy to find these days because this is Jupiter. And so these are the stars of Eastern Gemini. Yeah. Here, better take this back. All right. Take this like demon machine back. It wants me to get going. I knew you'd been talking. So it's relatively near Jupiter. These are the stars of Western Gemini. The Eskimo Nebula is down here. And so it's a quick, you know, you can get there from there. And so that's a pretty nice, I think that'll be a fun double star to look at. Next slide, please. Now that you got the clicker, there you go. Algol has a couple of easy minima. One on Saturday, February 21st, 9:13 in the evening. The other one is on March 16th. It was a little bit beyond the next meeting, but I put it in there anyway as something to look forward to, 8:45 p.m. I think I've got one more slide before the challenge objects. One more slide. So there's an interesting comet inbound towards the sun, comet 2026 A1 MAPS. It's a Kreutz family comet. They are sun grazers. Think IKEA Seiki in 1965. They are known to become brilliantly bright, assuming they survived perihelion passage. So perihelion for this guy is on April 4th. It may be visible in full daylight. I never saw IKEA Seiki. It was just before I started to get into astronomy. But I've read about it, and there are some estimates that put its brightness at minus 10th magnitude as it rounded the sun. It could be seen with the naked eye. Now, of course, right? Careful, because that's really, really, really close to the sun. But I think on April 4th, if it survives perihelion, and you shield the sunlight like with the side of the building, something appropriate, you might actually be able to see the comet with the naked eye. Maybe. Anyway, it won't be very visible at night, but there's a chance we might see it. So we'll talk more about that as we get there. Glenn, you do some talking.
Now some deep sky talk.
Oh, I love this stuff.
We're starting again the Observers Challenge. It was started by Roger Ivester, and they ran their course just last year. So we're starting all over again. And actually, they started, I think it was February of, I'm going to say 2009. So we didn't have a January object. So Rich and I kind of decided on Messier 74. But I did want to say, now that we're going back to the beginning of the Observers Challenge, these are going to be easier to observe objects. And some of the stuff we were throwing at you last year was pretty hard to see. These will get pretty easy. In fact, the three I'm going to show you, I've seen all three with a 3-inch reflecting telescope, so they are easy targets. Even M74, it has that reputation of being the most difficult, or one of the most difficult of all the Messier objects. I did pick it up with a little 3-inch reflecting telescope. In fact, I've got some pictures here. Let's just go on to the next one. All right, this is Doug Paul. Wait a minute, this is M74. This is Doug Paul's image. Want to say anything about the image? Then go ahead. We'll go to the next one.
I said Doug here.
There's Mario. I know we weren't giving the particulars like we used to, in all fairness, because the meeting, we're at the end of the talk right now, so I just want to go through a little bit more quickly. I did want to make one comment that we didn't get a lot of observations of some of these objects, and I think it's been either so cold or again, some things are so difficult, but those are the ones from the last time.
This is just, if you do hyperbolic stretch, I think that's what NASMS does, but I don't think the image is clear. It is much more, there's a lot more details you see on the left. If you don't do it right, you get what I did. Anyways.
I'll tell you what, it's
They actually both look pretty good.
It's a beautiful object, definitely. Okay. And this is just a sketch. This is out of my notebook from years ago. This is back on my birthday in 1981. And this was the observation of the 3-inch reflecting telescope. And the same I just made a comment. It's even tougher to me than M76. M76 for some reason had a reputation of being pretty tough too. I saw those two in the same night, so it was a good evening for observing. Now let's go to the one that's going to this month. And this was the first of all the observers' challenges way back in 2009. We're bringing it back again, the Crab Nebula. So we encourage you all to go out now. And when the weather's been cold, but give it a shot. We'd like to see some images and some sketches, if you have them, of the Crab Nebula. It's a supernova remnant. And it's just about a degree from Zeta in Taurus. So you could actually you just focus on Zeta and just kind of squirrel around, and you catch it on the side just about a degree away. So it's not that hard to find.
It's
Next,
6 by 4 arc minutes, so it's a fairly good sized object, which means it's got a relatively low surface brightness. It is a challenge object, but be patient. Use all the tricks you know, filters, jiggle the scope. You guys all know, folks all know about jiggling the scope, right? Especially the human eye is very good at seeing movement in the dark. So if you jiggle your scope a little bit, let the star field kind of jiggle, sometimes the faint object will pop up.
And next month, now Rich, you've never seen 24
I have not.
have you?
I have not.
And I could give one reason why a lot of people haven't seen it. It's way the hell out of nowhere. Here's the bowl of the Big Dipper, and it's kind of there's a star over here, but it's one of the stars in Camelopardalis. And Camelopardalis is such a faint constellation. Anything that's in Camelopardalis, I've looked at double stars here. It's a real project to try to find it.
Nobody knows where Camelopardalis actually is.
It's that void in the sky between the constellations.
Exactly. But I will tell you this though, I did see it with a 3-inch again. It's actually a fairly bright object. It's about like 9th magnitude, so it's not that difficult. I think the part that I saw was probably the nucleus of the galaxy. It's fairly large, but I would have to think that the nucleus is fairly bright because that's what I saw with a 3-inch telescope. But again, I'd just like to encourage you to make your observations, send them in to me, and I'll put them in next month's slideshow. And as always, thank you, and keep looking up.
Here's Mario's image. Here's Mario's image.
Oh,
2403.
okay. And I'm sure that the part I saw was right about probably this part right here.
Yeah.
It's probably too faint to see in a small scope. But again, the problem with that one, the challenge is finding that thing. You got to do a huge star hop to get there. I don't know how I found it back then, but I did. So I know it's doable again.
Give it a try. The observing nights that we have scheduled up and coming are this weekend, and then another 2 in March and 2 in April. Steve and I are going to make some command decisions about this weekend as far as the clubhouse being open. Every time it snows, the fields get covered with snow. I was up there last night for merit class. It's very slippery. Underneath the snow, it's icy. The observatory is probably not going to be open, and you'll have to shovel out a space if you want to set up a telescope. But we'll see. It's supposed to be pretty nice on Saturday night. So maybe Saturday be a better of the 2 nights. Watch your emails for whatever decision is made. And then I think it's on to the outreach stuff. Corey, do you want to talk about the I Heart Science Festival? You were there with Kira and Bennett.
Thank you, and keep looking up.
Hey, Glenn, thank you very much. Love to have you back. So I see you're over by the goat again.
Yep, all the mammals. So the Harvard Natural History Museum invites a bunch of local science clubs to set up tables and show what they're about. They invited us this year. So we brought some star charts, some books and photos. Unfortunately, we don't get to go up and look at the stars middle of the daytime inside a building, but we do get to show sort of what our club's about, the stuff that we do, general amateur astronomy, and I brought some optics to the table to try and explain to people how the telescope formed an image, and it was a lot of fun.
Great, thanks for being there. Thank you, appreciate that.
So next month, we have John Soroda from MIT Haystack talking to us. So hopefully all of you can come.
Thank you, be here.
All right.